technicalities of Zoom today. Welcome to the Data Science Seminar Series from the University of Washington eScience Institute. I'm Nicoleta Cristia. Today we will watch together two presentations from one of the eScience Institute core programs, Data Science for Social Good, or DSSG for short. The DSSG program enables novel research on focused collaborative projects with an applied social good dimension. Each year, up to 16 student fellows are selected to work on data-intensive projects that have concrete relevance and social impact. Students work closely together and are coordinated and advised by data scientists for a 10-week period over the summer. If you'd like to learn more about our nice and wonderful program, please go on the eScience Institute website for more information. But today we will be hearing from two DSSG teams and their projects that were developed over the summer of 2022. We will start with the first team, composed of Vidisha Chowdhury, Mehdi Gomer, Philippe Schicker, Shamsi Soltani, and coordinated by data scientist Nicholas Bolton. The presentation was previously recorded, but we have here three team members today, Vidisha, Mehdi, and Philippe, who will answer your questions at the end of the presentation. The title of their talk today is Heating Loads in Alaska and Beyond. The second project from the DSSG program is titled Satellite Streaks in Astronomical Images. Team members for this project include Abhilash Biswas, Keanta Chambers, and Ashley Santos, advised by data scientist Vaughn Iverson. Abhilash is here with us today and will address your questions as well. And to do that, please don't forget to use the Q&A feature of the Zoom webinar version to ask questions. And with that, I'm going to ask Dave to share the screen. He already did that, and start the first presentation of today. Thank you.
Hi everyone. Thank you all so much for joining us today, and we'll be kicking it off. So the first presentation is about the project titled Heating Loads in Alaska and Beyond, and I'd like to start off by introducing the team. We've got our team lead Erin, our data scientist Nick, and from left to right the fellows, myself, Philippe, Maddie, Shamsi, and Vidisha. We have affiliations with a number of institutions, including the University of Washington, the University of Alaska, Stanford University, and Carnegie Mellon University, and bring subject expertise in areas such as economics, engineering, public health, machine learning, and regional Alaska expertise. For context, global warming is the most pressing challenge of our generation. It is happening approximately 4 times faster in Alaska when compared to the global average. There's a huge and increasing urgency to decarbonize energy sources, particularly in Alaska. And in order to reduce the accelerating impacts of climate change, reductions in emissions are vital. And therefore, national and local decarbonization is critical. Our work initially focuses on Alaska's Rail Belt region. The Rail Belt electrical grid region is defined as the service area of 6 regulated public utilities that extend from Fairbanks to Anchorage and the Kenai Peninsula. Residential and commercial heating make up large parts of the contribution toward global warming. And a large aspect of reducing energy and heating use is first understanding the current state, and thus this project aims to drastically improve the way heating loads are estimated in Alaska. Alaska has unique needs and challenges relative to the rest of the United States. For example, Alaska has far less centralized energy, a large culture of independence, and much colder temperature in general. And so the lack of centralized energy information is a key reason for this project in the first place. And so therefore, we aim to fill this energy use data gap in order to better understand the current state of energy and heating needs in Alaska. We do so by taking a geospatially informed approach. This means we use large-scale satellite data to get information with high granularity. In preparation and during this project, we have met with various Alaska-based researchers and experts to gain a better understanding of the current state of energy needs in Alaska. We've had individual meetings with researchers from national renewable energy laboratories. We met with scientists and Alaska heating experts, and we also had group meetings with experts from the University of Alaska and other parts of Alaska who are very well versed in the current literature and scholarship. Our work is in contrast to that current scholarship and research being done, particularly in this region. At the moment, micro-level approaches, meaning very time-intensive, on-the-ground approaches, are the only ones yielding results. So this means researchers go to individual houses, take measurements, install meters, and wait for months for results. In contrast, our top-down large-scale approach allows us to estimate the heating needs for large parts of Alaska. This work has immediate impact since it will enable researchers to do large-scale calculations for all of Alaska, which is previously not been possible. Additionally, results can be used for immediate sustainability and decarbonization policy implementations. And lastly, this approach can be expanded to the greater Arctic region, which shares similar challenges. So our task was to create a model that predicts heating loads for buildings, whether that be commercial or residential, in Alaska, accounting for very local climate. And we start off by doing a focus on the Rail Belt.
So what are heating loads? For our project, we define heating loads as BTUs per year and alternatively as BTUs per year per square foot. And a BTU, because many aren't familiar with that unit, it's a British thermal unit, and one of them is roughly equivalent to the energy released when you burn a match. And for reference, a heating load for a 1,500 square foot building can range between 45 and 90,000 BTUs per year. So that example I gave, there was a range of heating load, and that's because there are a lot of things that contribute to how much heat it takes to heat a given space. So for the purposes of our project, we went with these four variables that we would need to be able to estimate heating load. So the first is local climate conditions. This is pretty intuitive. If it's warmer out, there's less energy needed to heat your home. And we also needed the height, the base area, and the age of a building. What you'll notice about all four of these is that we can approach them geospatially. So that lets us use that large scale approach that Philippe described. A very broad flow chart of the process we're embarking on. First, we take building features, that's the building age, height, and footprint. We add to it climate features that we generate out of many years of climate data, combine them into a sort of model, and the output from that model will be heating load in the form of BTUs. To go a little bit deeper into the work, we're actually using a supervised learning model. So supervised learning needs output data to train on. Here, that's heating loads. And as Philippe described, there is no ground truth estimate for heating because that work is very, very challenging and we don't have it for large regions. What we do have are current estimates from researchers that have created regression equations for both Anchorage and Fairbanks to give some sort of continuous BTU estimate for buildings in those cities. So how does our model learn? So what we do is capitalize on the climate differences between those two cities, which as you can see are in different regions of Alaska. And then we generalize to the rail belt that has all sorts of different climate variation.
The extraction of building features from geospatial data was one of the biggest and most challenging aspects of our project. For this, we used Google Earth Engine, which is a cloud computing platform that allows one to access and analyze geospatial big data. The public data sets we used from Google Earth Engine's archive consisted of satellite images captured across time, as well as geometries of building outlines in Alaska. We had to aggregate these data both temporally and spatially to arrive at building level features and then export these as tabular data for analysis. The next slides describe this process further. A key advantage of using geospatial data is that it not only allows us to identify where buildings are, but also estimate their ages and dimensions. A building's age or year of build may be important for estimating heating needs, as it may be correlated with air leakage. We estimate a building's age using data that tracked changes in land vegetation since 1985. Similarly, a building's height and base area determine its volume and thus may affect the amount of energy required to heat a building. While building heights were calculated using land elevation data, areas of building bases were estimated from building outlines. The shapes shown in orange in the map on the right are examples of building outlines we used. An important aspect of our model is that it uses local climate variables to predict heating needs of a building. The climate around a building is likely to influence its heating needs, and local climate may vary significantly within a state. By mapping land surface temperature data over building outlines and aggregating them over time, we construct heating and cooling degree days for each building. Degree days are simply measures of how cold or warm a location is. The more extreme the outside temperature, the higher the number of degree days, resulting in higher levels of energy use for space heating or cooling. The map that you see on this slide is a zoomed in version of the annual heating degree days mapped over Alaska. The variation in colors on the map correspond to the variation in local climate observed in the state. Pink denotes higher absolute value of heating degree days, that is, areas which need more heating. While climate is subject to cyclic fluctuations over time, the climate pattern observed in the recent decade may differ significantly from earlier ones due to climate change. Therefore, it is hard to say if more recent climate data or longer run climate variables would be better predictors of heating needs. As a result, using data from 1981 to 2020, we created 10-year as well as 30-year averages of degree days, which go as inputs into our model. With data on building features, climate, as well as simulated data on heating loads, we try to estimate a model that can predict heating loads at the building level. We explored a range of models, which include ordinary least squares linear regression, ridge regressions, with and without polynomial features, decision trees, and random forests. We evaluated these models using their mean squared error on the test data. Each model's mean squared error is listed on this table, and one can see that it keeps reducing from top to bottom, showing that the random forest regression performs the best. A point to note here is that we are yet to explore a wide range of models and intend to do so as we get access to a more comprehensive heating loads database. On this slide, we try to explore which features are actually important in predicting heating loads as a part of the random forest that fitted our data the best. The y-axis shows various features which were included in the model, and the x-axis shows their importance on a logarithmic scale. Feature importance can be described as a score assigned to features based on how significant they are at predicting a target variable. From the graph, 8 seems to be the most important predictor. This can be expected as older buildings might be less energy efficient and more prone to air leakage. However, this may also be due to the output we used for model training, as it was interpolated from regressions of heating loads on age. We also see that heating degree days averaged over 1981 to 2010 and 1991 to 2000 are relevant in predicting heating needs. This highlights that it may be important to take both recent and older climate data into account while estimating heating needs. While these results are a part of a proof of concept exercise, they do have the potential to inform decarbonization policies like energy retrofitting in Alaska. For instance, the importance of the age variable as a predictor may answer if it is better to replace old buildings rather than retrofit them to save energy.
As Vidisha has shown in the last slide, we see that age and location-based climate data are the features that are most informing our models. As such, it's important to ask the question, what happens when we change how we're sampling these features? The basic idea behind data sampling is to balance the data that you're working with across a number of different factors. And the motivation behind this is to avoid biasing your model towards particular types of data. For example, in this project, we explored balancing our data over location and over building age. What this means is, for example, Anchorage and Fairbanks. Anchorage has a higher population than Fairbanks. As such, there are more buildings located in Anchorage than there are in Fairbanks. So without balancing our location-based data, our model is receiving more input on heating load needs in Anchorage than it is in Fairbanks. So to balance these, we upsample Fairbanks to make sure that the buildings coming from Fairbanks and the buildings coming from Anchorage are the same amount, so our model is not being weighted in any particular way towards location. From doing these results, we can compare what balancing location and balancing age and how that affected our different models. As we can see, balancing location improved the models, specifically the decision tree model and the random forest model, giving a much lower mean squared error for both of those models. And balancing across age, so making sure that we're passing an even distribution of building ages to the model, improved all of the different regression models. So we can see from this that balancing the data is definitely an important factor and can improve the heating load estimates that we're outputting. During this project, we have generated heating load estimates using our model that capture the variation in local climate. In addition to generating these estimations using past and current climate estimates, we also predicted heating needs for future climate estimates. All of this work is filling a vital information gap in the field of heating and decarbonization in Alaska, and can now be used to inform relevant policies and inform the way towards decarbonization in Alaska. Throughout this project, we've faced challenges, including challenges regarding the data and ethical challenges. For data challenges, the Arctic region specifically has particular challenges associated with collecting data there due to like specific regional weather patterns and things like that make it a unique area. As a result, our team has had to overcome this issue, and our solution was to take into account multiple different data sources for the data that we needed for our model to combat the fact that many of the data sets we were looking at were sparse in certain regions. In addition, we also encountered some data-related challenges while using Google Earth Engine. While Google Earth Engine is a great tool for large-scale geospatial analysis, the number of buildings and building features that we were looking at in this project is particularly large. We were looking at over 100,000 buildings and approximately 10 features per building that were quite detailed. As a result, we faced some challenges when trying to export the data from Google Earth Engine to pass it over to our model. The solution to this was to optimize the way in which we were exporting our data. Some of the ethical challenges that we faced on this project include the fact that we're working with large-scale geospatial data that's open source. Due to the open source nature of this data, it is impossible to collect any sort of community consent about the information in the data. And so, as such, as researchers in this field, we need to make sure to tread carefully and be transparent about how we're using this data. In addition, our top-down geospatial approach required assumptions as we went along. For example, our model assumes that the heat needed for the third floor of a building is the same as the heat needed for the first floor, which is most likely not true considering that heat rises. and the third floor probably wouldn't need as much heating as the first floor. However, this was a simplifying assumption that we had to make in order to complete this project. These kinds of assumptions all require transparency on our part as researchers. While this project was only 10 weeks, its work is very important, and several of us will be continuing on the project. As such, we have a number of different tasks we'd like to see completed in the field. First off, we would like to incorporate the retrofit database that Vidisha talked about earlier. We think that incorporating this database into our model could tell us more about how effective retrofitting really is, and it could possibly affect how important the building age variable is that we saw in our feature importance analysis. In addition, we want to add more climate simulation models into our model, particularly those with higher spatial resolution, which will give us more accuracy and tell us a little bit more about the differences in weather between all of the different areas in Alaska. In addition, we did not have a chance to do a full sensitivity exploration of our models, meaning we didn't get to explore, for example, the assumption I stated earlier about building stories needing the same amount of heat. Finally, when talking to researchers about what they wanted to see come out of this project, one of the specific things that was noted was hourly heating load estimates. This is definitely possible to do from the information that we've gathered on this project and would not be too challenging, but it's a next step that we'd like to take in order to continue our relationship and collaboration with relevant researchers. Finally, other Arctic regions and the rest of Alaska can benefit from this work as well. It's very relevant and clearly important, as Philippe said, since global warming is one of the biggest problems of our generation. At this time, we'd like to thank our supporters of this project, the University of Washington, specifically the eScience Institute and the Data Science for Social Good program, and Micron. We'd like to thank all the attendees today for coming to hear about our project. We really enjoyed working on it this summer.
Great, thank you very much for your presence here. In the meantime, I think everybody's here, all your team is here today to help discuss this project and answer questions. And I think I'd like to start with the questions that are already in the Q&A box. I can start reading them to you. The first one is from Keisha, and she's asking, how did you think about correlation among your features in the models, especially the local climate data sets in which you used overlapping time windows? If any of you would like to talk about this.
I can talk about this a little bit, and then maybe some of the other fellows can jump in if they want to add anything. Yeah, so I guess the short answer is that we didn't really consider this in the work that we did this summer. The 10 weeks really flew by, and this preliminary work was to show that we could accomplish a goal of generating heating load estimates using the top-down approach that we explained in the presentation through using Google Earth Engine. But I think that your point is a great next step and should be added to our list of future work tasks.
Yeah, good point. Here's the next question. Could you please mention the size of the data? How much was the training versus the test? Sorry, I couldn't recall. Could you comment on the split?
Yeah, so if I recall, we were looking at over 100,000 different buildings between Anchorage and Fairbanks. And I believe that we went with a standard 80-20 split for our preliminary work. But other fellows, please jump in if that seems incorrect. I'm pretty sure that's right.
No, I just want to say that that sounds correct because based on the basic count of the buildings that we had looked at, I guess that sounds pragmatic.
Thank you. I think we're going to take this last question from Ben and move on to the next project. It is important to differentiate between different heating sources and electric versus gas versus oil. And if you could comment on that.
I can speak to this a little bit. One of the really interesting things about Alaska is that utilities are not centralized in the same way that folks might be used to in the mainland. And because it's such a harsh environment, a lot of people have redundant like backup options for if electricity goes out and there's documented a lot of power outages, you need some other way to generate heat for your home for safety reasons. So that makes this particular question really difficult for Alaska. We discussed it a bit with subject matter experts, but sort of our project is placed in this space where we just want to quantify what the heating need is before we necessarily have an intervention to you must decarbonize this thing right now, because what is lacking is just any understanding of how much energy is needed, regardless of the actual source, if that makes sense.
Yeah, to add on to that, I think like this project in particular was kind of the first step in creating an understanding and contextualizing the current state of heating needs before we can move on to like decarbonization options. It's really important to like understand obviously where we are right now, and so that's kind of where we were over the summer.
Great, thank you. Thank you for being here today with us. And now we're gonna hear about satellite streaks in astronomical images.
Project presentation. We are the Satellite Streaks team. My name is Kilando, and I'm joined by the other two fellows here, Abhilash and Ashley. You can probably see them waving on the Zoom screen. We also have our project leads and data scientists, Dino, Meredith, and Vaughn, who are very integral in helping us accomplish this project. So today we will be discussing the problem, our project and its output, the process behind our summer project, and future work that we intend to impact. So at this point, you're probably wondering, what about satellites impact our ability to perform social good or mitigate social harm? And a lot of people may have this question because they're familiar with satellites as being revolutionary in many arenas, maybe revolutionary in the space race with the release of Sputnik by the Soviet Union, or revolutionary with the geostationary satellites that give us GPS navigation. And some people understand satellites to be integral providers of wireless communications and connections such as the internet. But a lot of people aren't really aware that satellites can and do inhibit human beings from being able to access the natural resource that is the sky. And the particular satellites in questions that do this are low Earth orbit satellites. So low Earth orbit satellites are highly reflective of the sun's rays, very similarly to how the Earth's natural satellite, the moon, functions. But unlike the moon, they rapidly orbit the Earth in the span of 30 minutes. And as such, low Earth orbit satellites are visible to the naked eye, posing a threat to nature, culture, and astronomers. In terms of culture, there are global indigenous populations that rely on the night sky as a traditional religious and cultural resource. And the visibility of these low Earth orbit satellites pose a threat to the integrity of this resource, especially since these traditions are passed down orally. In the words of Professor William Sutherland, in terms of nature, low Earth orbit satellites may mislead animals from responding to celestial cues. And in terms of astronomers and astronomy enthusiasts, I want to reemphasize that these low Earth orbit satellites are highly reflective and very fast in their orbits. So in order to demonstrate that, I'm going to show you all a visualization. And as you can see, there are flashes going across the sky here. And those are actually satellites that are visible. And as you can see, they're very bright and very fast. And when telescopes take images, they don't do so instantaneously, but they take a few seconds to actually capture the image. And so those satellites end up appearing as streaks. So to demonstrate what a telescope image would look like, this is an actual telescope image. And this image, as you can see, has a few dots that represent stars and celestial bodies, but more importantly, it also has satellite streaks going across the image. And these satellite streaks makes it very difficult to just explore space for astronomers and for astronomers to also learn more about the celestial bodies that are surrounding us. So we also want to emphasize that the problem isn't just satellites, because satellites aren't inherently bad. As mentioned, they allow us to get great innovations, but the problem is the exponential launch of satellites by commercial aerospace companies. So as you can see in this graph, we have the number of untracked objects and the number of tracked objects in Earth's orbit. And as you can see, there's a general uptick of most of the objects. However, if you look at the blue line at the bottom that says active, this is representative mostly of low Earth orbit satellites. And as you can see, there's an exponential growth in the recent years of the amount of satellites that are being released into orbit. So if I have not convinced you of the gravity of the situation yet, I'm going to show you a simulation, and each of these pictures are simulations of the Earth, and surrounding the Earth are dots. And each dot represents a satellite, and the color of each dot represents the company that has launched or intends to launch the satellite in question. So in 2019, we see there are some, but not an overwhelming amount of satellites in the Earth's orbit. But in 2021, we see that there is an exponential growth, and this is the true amount just last year. And in 2023, although 2023 has not happened yet, these are estimations based on aerospace companies filing with institutions about their intentions to launch satellites. We see that there is a striking amount. And in 2025, the exponential growth is so visible that the Earth is covered with a cloud of satellites. And we also want to discuss the fact that there are no regulations on the brightness or numbers of satellites that are launched by these companies. So to reiterate the problem, there are a large number of low Earth orbit satellites, and as such, this creates streaks in astronomical images, making astronomy research for both astronomers and astronomy enthusiasts very difficult. So hopefully I've convinced you that the satellite streaks are definitely a problem. So let's examine how our team's project attempts to address this problem.
Great, thanks, Kilando. So with that overview of the problem, we believe that one of the first steps towards tackling this issue is sort of quantifying the impact of this problem, such as quantifying the properties of the satellites, quantifying to what extent do they damage the astronomical images. And that is specifically the motivation of our summer project, which is to detect and quantify satellite streaks in astronomical images. So in terms of the current work done on this topic, we have astronomers tracking individual constellations of satellites such as Starlink, and we have telescopes that regularly capture images containing satellite streaks. And what this data leads to is analysis of this kind where certain properties of the satellite streaks are quantified. However, one of the drawbacks is that these are mostly like bespoke, manually done analysis that cater to the specificities of that particular image or that particular telescope. And we want to take this forward by scaling up this process and making it more generalizable. So starting with the current body of work, we want to leverage computer vision algorithms and create a generalizable tool that can take in a wide variety of images containing satellite streaks from a range of telescopes on Earth and obtain basic information on these streaks properties. And as a next step, like there are many use cases for this basic information. One of them, for example, is that we know a lot of satellite operators are currently working on mitigation strategies to reduce the brightness of their satellites. And this tool could provide at-scale information to these operators on whether their mitigation strategies is working or not. So with that overview of like our goal, I want to present you our output from this summer project, which is a Python library called SatMetrics that can detect and quantify satellite streaks in astronomical images. We use an open data repository for astronomical images affected by satellites called Trailblazer to build this tool. So at a high and simple level, the SatMetrics library can take in like a wide range of images containing satellite streaks And if like those images have a streak, then detect that streak and output basic information about the streak that can lead to further analysis downstream. And all of this is towards the hope that like generating more information and more analyzable information on this topic can draw more attention towards this problem and probably support like possible policy interventions towards this issue. So now I'm going to spend some time talking about our process of how we built this library. So at a high level, there are three basic steps that we follow to create this. The first one is detecting straight lines in images. The second one is validating those straight lines to differentiate them from noise. And once validated, like we want to measure the properties of those streaks. So I'm going to talk more about the detecting lines part. To begin with, like detecting lines or straight lines in an image basically means like finding which pixels in that image contain that straight line so that we can study the properties of those specific pixels. So we use a widely used straight line detection algorithm called Hopf transformation to build this tool. So over here in this image, it's an example image. It's binary. So all the dots that you're seeing are like the only non-zero pixels in this image. And essentially how Hopf transformation works is it counts the number of non-zero pixels on every possible straight line in an image. A possible straight line being a collection of at least like 2 points. And more the number of non-zero pixels in a straight line, the higher chances of the algorithm voting it as a possible line. So as you can imagine, with the existence of noise in an image, the accuracy of this algorithm goes down. So along with returning what actually is the streak or the straight line, it can return a bunch of like false lines that essentially just represent noise. And that is the key challenge that we deal with in this part of the process. So on the screen, you can see like multiple real astronomical images containing like a wide amount of noise and differing like noise to like, pixel noise to streak brightness intensity. And consistently removing noise in like these wide range of images so that we can detect lines in them is the biggest challenge for this step. So we use various standard image processing techniques to like deal with this problem. And I'm not going to go deep into like each of these methods, but I'm going to motivate all of these by walking through an example. So on the left, we have like a original astronomical image with like containing multiple streaks and a lot of noise in the background. As a starting step, we try to estimate the background in this image so that we can remove that from the raw image. So on the right, you see like the image where the background of the original image has been estimated and removed. And you can see like some reduction in the amount of noise. Once we do that, like we apply binary thresholding and adaptive blurring of the image to progressively reduce noise. And one of our key assumptions around these steps is we expect the satellite streak to be like on the brighter end of objects in that image. And finally, after applying edge detection, we apply the Hopf transformation algorithm. So you can see the image on the right, where we have like the straight lines being detected and returned by the algorithm. One of the challenges that we face that is again related to noise is sometimes when there's like a lot of noise surrounding like a satellite streak, we can have like multiple straight lines returned that essentially represent the same single streak, as you can see in this image. And to tackle this problem, we use like a clustering approach that I'm going to like demonstrate through like a different example. So on the left, you have like another example of an astronomical image containing a streak that does not go through the entire image, and you have a lot of noise surrounding that streak. And on the right, you can see what our algorithm returns as straight lines. So you can see that the actual streak line is returned, as well as a bunch of other lines are returned, which essentially represent noise. So we try to cluster these into groups, where each cluster essentially represents like either a single streak or a collection of noise. So on the left, we have the straight lines returned, and on the right, we have like successfully clustered it where like the actual streak is contained in a separate cluster and we have noise in a bunch of other clusters. And the reason we do this is because we have validation algorithms downstream that can separate like noise from straight lines, but we don't want to waste computation by running that algorithm on every single detected line. So when we divide it into clusters, we can apply that algorithm at a cluster noise, cluster level, and like perform our validation. So I'm going to pass it back to Kilando to like speak more on this part.
Thanks, Abhilash. After we found clusters of Hoff lines that may represent a streak, as Abhilash said, we want to validate that what we've actually found is a streak. So to do so, we take the median pixel values of each row of an image and analyze the profile of that data. We look for key elements such as, is the fit of the profile approximately Gaussian? And if so, does that profile have an amplitude or a width that is characteristic of what we think a streak would look like? But before we can perform validation metrics, we have to rotate the streak. Our goal is to rotate all of the streaks in an image such that each streak is horizontal, and we crop those streaks so that they're the only streaks in the rotated image. So when Hoff lines finds the streaks, they find them in polar coordinates. So we start by finding two Cartesian coordinates of the line. We choose 2 points, the point at which the line enters the image and the point at which the line exits the image. We use those 2 points to calculate a slope, and then we use some basic trigonometry to calculate the angle of rotation. But when we rotate the angle, when we rotate the line about the angle and the image, it only rotates at the center point of the image. And so it's very difficult to find where the rotated line actually is. So to mitigate this problem, we basically set an anchor point, which we decided would be the midpoint of the line. So when we crop the image, we can easily locate where the rotated image is and crop it so that it only contains the streak. In cases when there are more than one line in the cluster, we take the mean, entrance, and exit Cartesian coordinates and perform the same computations.
So just to reiterate, rotating streaks allows us to do efficient streak analysis. So now that we've figured out how to rotate the streaks, we can now take an image and plot its pixel intensity values. The point of plotting pixel intensities is to tell us what and where the brightest object is located in our image. We take the median of the pixels because since a streak is consisted of clustered and extended pixel intensities, it offsets any outliers and gives us a more obvious peak. So in the top image, we have a bright star with some background noise. We see that the pixel intensity plot on the right side generates very narrow peaks, whereas on the bottom, the peak is more obvious in that it represents the streak in the image. Because this plot looks approximately Gaussian, we use a Gaussian as our model to fit a line through it and determine whether or not we measured a streak. So here we give an example of what a bad fit looks like. In the image above, we see that there's no streak, but rather just some bright stars and noise. Because there's no streak, the plot of this image contains narrow peaks and doesn't look approximately Gaussian. So when we try to fit a line through it, it doesn't converge and due to not passing our validation. So we would throw this plot away because this tells us that we're not measuring a streak, but rather some background noise, which based on the image we see here is true. So this means that this data is not useful to us and we would throw this one away and won't continue property measurement on this image since there's no streak. So what happens when we do validate a line within an image? The next step is to measure the properties and extract the quantification metrics of the streak. So here we have an image of the streak and its pixel intensity plot next to it. The red line on the right side of the plot is our fitting line, and visually we can quickly tell we have a good fit since the red fitting line is very close to the blue real data line. But what happened here statistically is that the normalized root mean square deviation, distance from the middle, and full width half maximum pass thresholds that pass validation. And since it validated and converged, we can confirm that we've measured a streak. So in this case, we keep this data and extract all the quantification metrics that Kilando mentioned earlier. Another great benefit of fitting a line through our data is that we're able to use these metrics to help further the rotation angle algorithm. Sometimes when we would rotate the streaks using basic trigonometry, the streak would not come out completely horizontal, which would make the property analysis less precise. To straighten the streak, we rotate the angle on the Hoff transform line with new angle calculations that are pretty close to the original calculated angle. Once we have our new angle calculations, we have to test them to see which one is the most accurate one that straightens the line. So here we see only 6 rotated iterations of one image. We apply the fitting function on them and assume an image with the smaller normalized root mean square deviation is more representative of a straighter streak to help us make the rotation more accurate. Here on the we see on the last image on the bottom right side has the lowest normalized root mean square deviation, and its line is fitted very closely to the real data. Because we see this, this means that the angle calculation that we have for this image or graph is going to be the best one for our rotation algorithm and allows us to measure our streak properties with more accuracy. So with all the work done within line detection, validating lines, and property measurement, we came down to our StatMetrics Python library that successfully outputs quantified streak properties from the images. SatMetrics is a public Python library that is meant to be used by anyone interested in analyzing satellite streaks and images, whether that's an astronomer doing research on satellites or enthusiasts who took pictures of the sky, noticed streaks in their images, and want more quantifiable information on the streaks. SatMetrics does not end here, though. There's still further developments that are important for our package. But before we dive into that, here's a quick recap of satellite streaks and astronomical images. The initial problem is that the industrialization of space makes the sky brighter, which causes environmental concerns, disrupts cultural traditions for communities, and produces satellite streaks and astronomical images, which makes studying the stars, galaxies, and our universe more difficult for astronomers. In order to study how streaks affect astronomy, nature, and cultures that rely on the sky, we first need a standardized set of measurements and analyses tools to characterize these satellite streaks, which is what our SatMetrics Python library is, a tool that outputs standardized sets of measurements in order to further analyses of streaks and images. So the next steps are a working solution. It's important to measure the brightness of our streaks, which are characterized through magnitudes, which are astronomical brightness units that astronomers rely on. We hope to use the measured pixel intensities to convert into magnitudes so astronomers have more additional useful information of the streaks. This will also help with evaluating if the streaks would be visible to the naked eye. So far, we've only tested our data on a variety of streaked images from the Trailblazer repository, but we want to continue testing this by creating test data sets and continue measuring the precision of the metrics. And finally, our long-term goal is to integrate our Python library to the Trailblazer repository, so when someone uploads their streaked images, our library can generate quantified streak data. Overall, we're very excited that our Python library could aid astronomers or enthusiasts in the research of satellite streaks so that they can come down to more feasible solutions at addressing the overarching problem of satellites. Thank you so much for your attention. We will leave the summary slide up for your reference. We're open to taking any questions.
Thank you very much, Team Satellite Streaks, for being here today and helping with the questions. There is one question in the Q&A box. If for some reason there were to be a stutter in a streak due to specific image stitching methods, would your program still be able to identify it, or would it result in the streak being missed?
Yeah, thanks. So I'm not like super clear like what a stutter in the streak means, but so it's difficult to give like a generic answer. But if a stutter here refers to like a part of the streak being wiped out because of our own like image stitching methods, like the answer is that it like depends. So as you would see, if you've seen the presentation and like the flowing example, as we progressively like clean the image and remove noise, we also do lose a few pixels that contain the actual streak. And as long as it's like only like a small proportion of pixels that gets wiped out, our program can still like identify the streak. But if it's a very faint streak and like the surrounding noise is like, you know, equally bright and like because of our own image stitching methods, we wipe off like a big chunk of the streak, then our program would likely miss it. And like, apologies if I didn't like understand the stutter word correctly, but if stutter means like something that happened to the streak in the original image that we are receiving from the telescope, then it again like depends on like what proportion of the streak still remains. Basically, like the method relies on like a number of pixels lying in a straight line to detect whether it's a streak or not. So if there are like enough number of pixels that still remain on a straight line, the program would still be able to detect it, but it's like a spectrum, and like as the number of like as the pixels representing the streak start going down, the ability of our program to detect it also starts going down.
Thank you, Abhilash, for addressing this question. I think we're at the end of our time today. I would encourage you to connect with our student fellows in the DSSG program if you'd like to find out more. If you have any other questions, please connect with them as well on their work. Have a good night, and we'll see you next time. Thank you.